A vector quantity has both size and direction. When giving a distance, we say how far and in which direction. Giving a velocity, we say what the speed is and in which direction we're going. Weight is a force which always acts downwards, and for any force, we give a direction in which it acts. There are many quantities which have size but not direction. One of these is volume. Another is speed. We may quote the top speed of a car, but we don't say which way it has to go. The mass of a quantity is given in kilograms and indicates the inertia to movement, but not movement in any particular direction. These are all scalar quantities. To get a total of two scalars, for example 2 volumes, it is simple addition. But with vectors, we have to take into account the direction in which they're acting. We're going to use distances on a map to illustrate this. If we wanted to travel by road from the house with the red circle up to the church in the village, being circled now, we would follow the roads like this. Each part of the journey is of a different distance and is in a different direction. But it's obvious from the map that we add these end to end. The resultant distance travelled can be marked on the map by joining the start point with the end point. That distance can be measured, and then the true overall distance calculated by using the map scale. The overall direction of our destination can be found by marking the north on the map and then measuring the angle between the north and the direction we travelled. This simple technique can be applied to any problem where we have to add vectors. In this example, an aircraft is flying due east, but is affected by a wind from the north. It's easier to draw vector diagrams on graph paper because then the scale is easier to interpret. At this scale of 1 centimeter to 40 kilometers an hour, the flight east will be represented by a 10 centimeter line. Adding to the end of that, the north wind will be represented by a 2 centimeter line. It's 80 kilometers per hour. The total velocity is found by joining the line from the start of the first arrow to the end of the last, from tip to tail. If we measure the length of that line and then convert it using the scale of 1 centimeter to 40 kilometers per hour, the 10.2 centimeters converts to 408 kilometers per hour. Rather than take the distance measurement from the diagram, which might be a little inaccurate, we can use simple geometry, in this case Pythagoras, to calculate that distance. Since this is a right-angled triangle, the hypotenuse squared will be equal to 400 squared plus 80 squared. The total of this is 166,400, and the square root of that is 407.9. Our original measurement was fortunately accurate. The bearing of the aircraft south of east can also be measured directly with a protractor, but in this case we're simply going to calculate it using tan theta. Tan theta is opposite over adjacent, which is 80 over 400. From the calculator, that angle is 11.3 degrees. So remember, you can add any number of vectors by drawing and adding them tip to tail. The final resultant is found by measuring from the tip of the final vector to the tail of the first. Thank you for watching.